asteroid with the planet. This story's had an interesting twist in the last couple of months, because actually another couple of amateur astronomers have detected another event in August. So it seems like perhaps asteroids are impacting with Jupiter the whole time, and the amateurs can see these events. They've never before thought it was possible to pick up these events. We might find that a lot more amateurs start looking, and a lot more of these events will be detected, and we might really start to get a distribution of the kinds of objects which are impacting Jupiter, and from that we'll be able to work out what kind of sizes of asteroids there are out there distant to Jupiter in the solar system.
Again, the amateurs lead the academics into interesting discoveries. That was Dominic Ford, and before him, Caroline Crawford and Andrew Bonson with a roundup of space science news. They'll be back later on to tackle your questions.
Expand your mind and Neptune in Naked Astronomy, the stellar space science show. For more episodes of this program, look us up online at nakedscientist.com/astronomy.
Still to come, we take a look at solar chemistry to find out how water can form inside a red giant star. But first, this month saw the European Planetary Science Congress, held at the Pontifical University of St. Thomas Aquinas in Rome. To find out what the Congress is and explore some of the headlines coming out of the event, I spoke to John Merrison, a planetary researcher from Aarhus University in Denmark.
It's a forum where planetary solar system research researchers can get together, present their work, discuss their results, and plan new missions, propose new missions, try to get on other people's missions, discuss the latest technology, instrument development. There's also students that come here, so it's an opportunity for them to learn a lot more about planetary research and put their work into perspective and get to network. There's also a lot of science discussion, and there's also a lot of missions and technology discussion.
And is it just delegates from Europe, or do you have people from all over the world?
No, it's very international. We are about 700 participants this year. There's been about 100 from the States. I don't know how many from the other countries, but there's been a lot of Russians here. They have their own proposals for missions. They've been active in their work. So although its central purpose is to network within Europe, it's certainly put on an international scale. And next year, it's going to be a joint meeting with the American DPS meeting. So that'll be very international.
So you have a range of professionals, academics and students there. Is it also open to amateur astronomers?
Yes, I know of at least one amateur who's presented his work here, and it's been very exciting. It's new impacts on Jupiter, and some of the activities here are aimed at getting amateurs involved in the science of looking at the solar system. They're doing a huge amount of observations, and this in principle is a resource that the scientific community really is excited about utilising. There are going to be meetings in the future. There was a spin-off meeting here this morning. It was all about amateur astronomers, how they can contribute to the science of planetary research.
And how's Rome as a setting?
Perfect, really. It's wonderful. It's very perfect, really. It's wonderful. It's very relaxed, and people can be outside and chat in a very relaxed way. We're right in the centre, so we're right next to the Colosseum, so everybody's been out late in restaurants discussing, and it's been very pleasant.
Nice chance to combine a bit of tourism along with your science. What have you been there for, first of all? What have you visited?
We have a ESA and EU-supported laboratory facility in Aarhus where we look at the Martian surface. So we have like a simulator facility, and we're also building instruments to send to Mars and maybe on other planets.
What do you think have been the most exciting news and the most exciting things to have come out of this?
Well, there's been a few events. Apparently there's a new model for how Phobos, one of the moons, was created. The latest results seem to indicate that it was maybe produced from an impact on Mars.
Rather like our own moon.
Rather like our own moon, yes, indeed. Mercury, the NASA Messenger mission is looking at some mineralogy of Mercury, and this is not fitting in with what they expected, so that's quite exciting. I think the scientific community is a little confused as to what all that means. They're looking forward to when the European Baby Colombo mission arrives, maybe it'll shed some light on that issue. Venus, there's been several good talks here about recent volcanism on Venus and lightning in the atmosphere. I think they're getting closer to understanding the rather complicated atmospheric circulation of Venus. Oh yes, and there's been some great pictures of the moon from the Lacrosse mission. Incredible resolution, lots of activity for upcoming missions to the moon.
John Merrison with a delegate's perspective on the European Planetary Science Congress. Now, how does water form inside a star? I spoke to Professor Mike Barlow from University College London to find out how they solve this problem.
Well, the problem that was revealed, and we got a hint of it about 10 years ago, was that the brightest carbon star, CW Leo, was found to have oxygen-rich molecules in its atmosphere, water molecules, along with carbon monoxide. They are the two most common ways you find oxygen in molecules around cool stars. Now, the problem that was encountered about 10 years ago, there was an American protocol for SWAS, which detected a single water life from a cool, low excitation level from this star. And it was so surprising because around carbon-rich stars, you should get all the oxygen locked up in carbon monoxide molecules. You shouldn't have any oxygen left over to form any other oxygen-rich molecules.
So this is because the ratio of carbon to oxygen suggests that all the chemistry will involve locking up the oxygen molecules, and we won't see them available for things like water.
That's right. That was the very simple division we had between oxygen-rich stars and
in that case if it's had enough time for the reactions to build up this much carbon?
Yeah, these are stars right at the end of their lives. Probably in the mass range of 1 to 5 solar masses. Unusable hydrogen in the core, they start breaking helium. And eventually they bring up, as I said, the products of helium going to the surface. They become very luminous at the same time. They become what's called a red giant star, a particular type of red giant star, which eventually will lose so much mass that it will become a planetary nebula. That's when the remaining star in the center contracts down, becomes very hot, and ionizes the ejected material. Eventually that star becomes a white dwarf. And that's got to be the fate of the sun in 5 billion years from now.
So how was the presence of water, this spectral indication of water, justified 10 years ago? How did they explain it?
Well, because it was unexpected, and because the chemical models for formation of molecules in the atmosphere of the star weren't able to enough water, they hypothesized that there might be a comet cloud around the star left over from the earliest stages of formation of the star. It's like a water cloud around the sun has been hypothesized. So they suggested that a very strong mass loss from the star would interact and hitting the comet clouds and releasing water molecules, which, because it was so far away from the star, they would be quite low temperature. And if you see the few lines like the line they saw. What's happened with Herschel, of course, is it's seen with its spectrometers, it's been able to see a much more signal wavelength, for instance, force code. And we've detected more than 60 different water lines coming from all levels of excitation.
So seeing this and seeing that this means that there must be water there at a range of temperatures, this suggests that actually the original hypothesis for how that star was capturing this water is probably not right.
That's right. It means basically because we're saying hot water as well as cool water. The only regions that are hot enough are deep inside the star's envelope, the outflowing wind itself near the surface of the star. So the water appears to be everywhere. So we've had to reassess, therefore, the models of how can we produce this water. And the only possible way to do it seems to be if we can use ultraviolet radiation to break up the carbon monoxide into carbon and oxygen atoms. That would liberate the oxygen atoms to react with hydrogen atoms and form water molecules.
So where would this ultraviolet light be coming from?
Well, the temperature of the star is only about 2,500 degrees, which is much too low to emit ultraviolet radiation. So we've had to look at other sources of ultraviolet radiation, and one region we know where you have lots of ultraviolet radiation is in the interstellar medium itself, because it's bathed in the light from many very hot O and B-type stars, which emit a lot of ultraviolet radiation. Now, the problem as it's perceived is how do you get this ultraviolet radiation penetrating deep into the star's envelope? And because what we have is a lot of dust in this envelope, which is basically carbon dust grains, which have been condensed out of the carbon-rich material. So normally, if you had a smooth outflow, the obscuration by the dust would prevent any ultraviolet radiation getting in. However, there are observations that point to the fact that the envelope around the star isn't smooth and symmetric. It appears to be more like a peanut or a bipolar shape. And that probably means that from some directions, the ultraviolet radiation encounters much less dust and can penetrate right down to the base of the floor.
Can we model this structure and work out if there would be enough UV getting in to create the amount of water that we think must be there?
Yeah, that's what we've done in the paper itself. Having put forward the hypothesis, we had to do some calculations and show that this was a plausible source. We know the density of ultraviolet radiation in the interstellar medium, so we needed to show that A, it could get down into the base of the star's envelope, and B, that the reaction rates would then be sufficient to produce the amount of water vapor molecules that we detect. And these calculations
hello.
some of the team
How are you going?
and they do indeed manage to produce enough water vapor.
So you got called into work, huh?
Any observational evidence that backs up the idea that the envelope would be this non-structure?
Yes, this object CW Leo is. Yes, this object CW Leo is a different.
Are you in there?
You cannot see it.
Are you just sitting on your bum up by stage door? Or are you somewhere else in the theatre?
However, when you image it at high resolution, high angular resolution, spectral resolution, you find that it's not a point source, it's actually several big clumps. And observations also in the near infrared show that you get almost like a peanut structure. So we know for sure that the envelope is not symmetric and smooth all around it, just from these imaging observations that we've obtained.
Would there be any other interesting chemistry going on that could help to confirm your hypothesis?
Yes, there are several other molecules have been predicted, and they actually are present in spectra, although they don't have as many strong emission lines as water does. So this is certainly going to be followed up further by high spectral resolution observations made with another of the instruments on board, Herschel, called HiFi, and it has much higher spectral resolution than the Pegasus and Spire spectrometers with which the current observations were made. So
Sometimes okay.
made of the hypothesis.
Mike Barlow from University College London explaining how ultraviolet light from distant stars can actually penetrate the clumpy envelope of red giant stars and alter the chemistry within. This is Naked Astronomy, the space science podcast from The Naked Scientists. If you've got any questions or comments for us, get in touch by email to astronomy@thenakedscientists.com. But now we return to Carolyn, Andrew and Dominic to take on your space science questions. Our first question this week came in from Ricky Dawson. He wants to know if starlight can be redshifted out into the microwave region. Dominic?
Theoretically, it wouldn't be physically possible for a star's light to be redshifted into the microwave region. the faster a star is moving away from you, the further its light is redshifted through the electromagnetic spectrum, and it could go all the way through from visible light right through to microwaves. However, in practice, I don't think any stars are moving away from us fast enough that their light would be redshifted that far. Now, probably the most well-known reason why stars have redshift is because of the expansion of the universe, and all the clustered galaxies in the universe are moving apart, and as they do so, they recede from one another, and their light is redshifted. But in order to be far enough away that its light will be redshifted right through to the microwaves, a star carries a distance of about 13.5 billion light years, and that means that its light would have to set off only about 1 million years after the Big Bang. And in fact, we think that stars took about a few 100 million years to form after the Big Bang, so there were no stars that early in the universe, and the earliest stars in the universe were at distances where they redshifted through to the infrared, but no further than that.
Of course, there was light around at those times, and it's what we now know as the cosmic microwave background.
What shows happening at work at the moment?
So that is exactly
anything interesting?
It ended up being redshifted all the way into microwaves, but it didn't come from stars, as Dominic said.
Where did it come from?
Well, it came from the fact that at very early times, everything was so densely packed together that it's in what we call thermal equilibrium. So actually, the energy that was in the protons and electrons and so on can easily be exchanged with energy and light, and everything kind of transfers between all the different forms of energy in that way. And so it's like a flash of that initial moment itself.
Thank you, Andrew. We've got a question actually that follows on from this from George Vulgaris, and he wants to know if light can become sort of diluted as well as redshifted.
Yes, that's absolutely right. So as space expands, not only is light redshifted, it's also diluted. So to get some picture of what's going on here, you could imagine a big box of ping pong balls. So you have got a transparent sealed box. You're shaking this box of ping pong balls, and if you imagine they'll all be bouncing around violently inside that box, so they kind of fill up the volume that's available to them inside that box. Now, somehow you could make that box bigger, then the balls overall would keep bouncing around, and overall they would be spread out through a larger volume as you make that box bigger. So mathematically, if you double the volume, then the density of balls would half. So it's similar for gas and, say, dark matter in an expanding universe. As the universe gets larger, it kind of spreads out and becomes less dense, it kind of thins out. And it is also true for photons. That's particles of light. They're diluted in exactly the same way. Of course, there's a complication with photons, because as we've discussed before, each individual photon is also losing significant amounts of energy through this redshift effect. So the overall effect as space expands is stronger than we predict from either the dilution effect or the redshift effect alone. You have to take into account both of these effects, and of course, that's exactly what we do with calculations.
Thank you, Andrew. We've had a question from Ron Bean. I've got this one to you, Carolyn. It says that tornadoes and cyclones rotate in a certain direction due to the Earth's rotation, but what causes galaxies to rotate in a particular direction?
This is a very interesting question. Of course, when we're talking about galaxies rotating, we're only really talking about spiral galaxies. Most galaxies are big elliptical shaped galaxies. No individual stars rotate around the centre of the galaxy. They're all moving in their own individual orbits, so go fairly random orientations. It's just when you get to a spiral galaxy, you've got like a ball of stars in the middle, and then you have this ordered rotation of orbit, the disk of gas and dust and young stars all rotating around the centre. And the key thing that sets up that rotation, it's something that goes right back to the individual hot halo of gas that the galaxy formed from. Because galaxies form as you have this 1,000,000 degrees gas, it condenses under gravity, you form stars at the centre, and stars continue to form out of the gas cloud. Now, if there's no inherent rotation in that cloud, stars will just rain down and you build up an elliptical galaxy. However, if there's even the slightest rotation on that original hot halo, say there's the tug of gravity from a nearby other hot halo just sends it spinning ever such a little bit, then as the cloud collapses, that rotation is going to increase. Just think of an ice skater pulling their arms in, they spin faster, it's just a conservation of angular momentum. And so their later stars form from a much flattened disk where the rotation is much enhanced. In terms of any individual galaxy, it depends on what the original protogalactic cloud is doing and the slightest movement within that. But as we talked about in the previous podcast, there's no preferential direction for the galaxies.
It's nice to think that the same basic physics applies to an ice skater spinning around as it does to a galaxy form.
Well, we hope so. Otherwise, we've got our models slightly wrong.
Dominic, we've had a question from Scott McGregor. He wants to know what impact a large coronal mass ejection would have. First of all, just remind us what this coronal mass ejection is.
Well, coronal mass ejections are massive bursts of ionised material that the sun throws off from time to time, and they come about because the sun is a highly magnetic object, but it's also got a highly variable magnetic field, and sometimes when the field suddenly sharply decreases on one part of the sun's surface, all of the energy that was in the magnetic field is dumped into the gas on the surface of the sun, which becomes incredibly hot and it explodes off out into the solar system in a sort of jet, which could potentially hit a planet like the Earth. Now, if people are exposed to the kind of ionised material coming off the sun, that would be incredibly harmful. It's rather similar to being exposed to radioactive materials. It's ionising, it damages organic molecules. But on the Earth, we're actually very lucky because we have 2 layers of protection above us. Of course, it's not luck, we wouldn't be here if they weren't there. But we have a magnetic field, which the solar wind particles actually can't penetrate. And we also have the atmosphere above us, which catches any particles which make it through the magnetic field. And that's what we see when we see the northern and southern lights. Now, in fact, even the astronauts on the International Space Station are relatively well protected because although they're above the Earth's atmosphere, they're they're still well within our magnetic field, which shields them from most of the radiation, and so they only receive about as much radiation as you get from travelling on an airline flight. However, coronavirus injections do have some effects. As the Earth's magnetic field does work on solar wind to deflect it away from us, that changes the Earth's magnetic field on the surface of the Earth, and that can induce voltages in long power lines, and if you're not careful, that can actually trip long-distance power distribution networks like the national grid. And every few years, there's an outage of a large power grid due to the voltages induced by that. One particular example was in Quebec in 1989, when a large fraction of Canada's power grid was knocked out by CME. Now, the CME also has great damaging effects on spacecraft outside the Earth's magnetic field. One of the most common reasons why a spacecraft could fail is that there's interaction between the electronics in the spacecraft, which is the particles, which actually changes the characteristics of the electronic components over the life of the spacecraft. And certainly looking ahead in terms of sending manned missions to Mars, this is going to be a huge problem. When we went to the moon, we were able to pick times when the sun was quiet, and there wouldn't be a lot of ionizing radiation that the astronauts would be exposed to. Going to Mars, it takes several years, and you won't be able to pick a time when the sun will be quiet for that whole 2 or 3 year period. And we're going to have to be a lot more investment in materials that can protect the astronauts before we could contemplate doing those missions.
Andrew, if we can come back to you, we've had a question from Rhys Hanan in New Zealand. Now, this one's thrown me completely, but he wants to know what Harava gravity is.
Okay, well, this is certainly an ambitious question. I mean, at its core, what Harava gravity is trying to do is construct a theory of gravity which is compatible with quantum theory. Of course, there's this big problem with physics at the moment that while on large scales we can describe the way the universe behaves and interacts through gravity using Einstein's theory of general relativity, if we try and apply that on very small scales, we start to get contradictions with this other great theory of 20th century physics, which is quantum theory, which describes how atoms and small particles behave. What it really comes down to is understanding the nature of space and time itself, because Einstein showed that gravity really is about the way that space and time are bent and warped. And so to understand what Petra Harava has been working on and why people are so excited, we need to think about the way that space looks on different scales. Now, the strange thing about trying to do this is that what we're actually talking about is the properties of empty space. So the properties of space if it had absolutely nothing in it. And of course, that's a bit mind-bending at first, because normally you try and think of space in terms of what stars or bits of gas or so on are doing. But really, we've got to talk about what an empty piece of space is like.
And we can't just treat that as a gap between the two particles we would normally understand, can we?
Well, in a sense, it's about asking, well, what is that gap? You know, if you say, can we treat it as a gap, then I have to ask you, well, what is a gap exactly? So if we want to understand anything, then understanding gaps might be a good place to start, right? So what this is about is, if you suppose you have completely empty space, so you haven't really got anything there that we can think of in concrete terms as humans, well, on different scales, then you'd imagine that that space has got to look pretty much the same. There's nothing in it. So if you take a magnifying glass and look at a really small patch of it, it's got to look the same, surely, as a pretty large patch of it, because there's nothing that gives you any indication of what the scales are. There's just nothing there.
That makes perfect sense.
It seems to make perfect sense, but actually, one of the things that comes out of Einstein's theory is that because of the speed of light being a constant, which is at the centre of Einstein's theory, if you change the scale of space, you also need to change the scale of time. So that means even for a completely empty box, if you double the size of that box, it's only equivalent to the original box if you watch it at double speed as well. Okay, so this does sound weird because there's nothing in there, but this is just about the properties of an empty space. Now, what Harava said is that perhaps on very small scales, this kind of scale no longer applies. So if you're looking at a very tiny patch of space, and you double the size of that patch that you're looking at, in fact, in Harava's theory, you'd have to watch it at 8 times the speed instead of double the speed. And it might seem like that's a totally arbitrary thing to say, but in fact, it has some kind of nice properties, because if you think of doubling the length of an edge of a box, then you've increased its volume by 8 times. And so what Harava is kind of doing is saying, well, let's do the same for time. Even though there's only one direction of time, let's increase that by a factor of 8 as well. So in some sense, it's putting space and time on a more even footing. Well, bizarrely, if you do this really weird thing, then still on large scales, you can find behaviour as predicted by Einstein's equations. But on small scales, you get very different behaviour. And what's really getting everyone excited is that you seem to get behaviour that allows you to build a theory of gravity that's consistent with quantum theory. So it's quite a difficult area, but hopefully that gives you some insight into what we're trying to do.
When you say small scales, how small is the size of an atom?
Probably the size of an atom, or in fact smaller. It's a tunable feature of this theory where exactly these effects start to take over and things start to change. Certainly you want it to be magnified by what we call the Planck scale, which is the scale at which currently gravity breaks down, but that's far, far smaller than the scale of an atom.
How long has this theory been around for? Is it fairly well accepted, or is it still quite controversial?
It's pretty controversial. It's been around since 2009, and it's just one, of course, of a whole range of different ways that people like to think about what gravity should maybe be doing on small scales. And of course, the most broadly thought about version of this is string theory. It's nice, actually, just to have an alternative to string theory, a new way of thinking about some of these old problems.
Thank you, Andrew. Carolyn, what should be a fairly simple question from Kishan. He says, how can we create a black hole?
Yes, the answer for Bond villains everywhere. Yes, how do you make your own personal black hole? Well, let's start off with what makes something a black hole. And the key thing here is density. You really need to concentrate as much mass or energy down into a small enough volume that the gravity is overwhelming and nothing nearby can escape the pull of the gravity. How we do this in space is you have a massive star, at the end of its life, begins to collapse under gravity, so it gets more compressed, the gravitational field gets stronger, and eventually you get to that point of where all the star's mass is pulled in beyond the event horizon. Gravity has overwhelmed everything. And the key point here is that gravity is doing the squeezing. So if you want to make a black hole, if you squeeze anything enough, if you compress it enough, you'll get to the densities required for a black hole. So for example, if you took the whole of the planet Earth and squeezed it right down to the size of a marble, that would be a black hole. However, to do that kind of squeezing, you need some enormous outside pressure or force. That's where the difficulty lies. So for example, start off with something really tiny, like a couple of subatomic particles, and you want to squeeze them together to form a minuscule black hole, perhaps by smashing them together in a high-speed collision. We can't even do that. The force and energy required just to squeeze them to that level is way beyond what we can provide.
This is what people were worried about with the LHC, of course, that we would be creating these tiny black holes, but the physics just didn't add up. It wasn't ever going to happen.
Well, it is interesting, though, that there are still get-out clauses, okay? Andrew's just been telling us about alternative theories of gravity. There is this remote possibility, and I will stress, I still think this is quite speculative, but how you could perhaps smash two subatomic particles together and get a minuscule black hole within the range of particle colliders. To do this, though, you'd have to rely on gravity behaving differently on sub-millimeter microscopic scales. And there are theories where perhaps on that kind of scale you've got extra dimensions and the gravity will be much more intense. So as long as you can get things close enough, you don't have to squeeze them so much before gravity starts to take over and do the squeezing for you. So it's still not entirely impossible that it might happen. And if it did, it means we'd learned a lot more about how gravity behaves on these tiny scales.
Of course, if we were to make a small black hole in something like the LHC, it would be a big problem, because there's a process called Hawking radiation by which black holes actually evaporate their mass slowly. And for a black hole of the kind of size that you would make, it would only last a 20th fraction of a second before it would evaporate back into the ether and not cause any problems at all.
Dominic, we've had a question here. Bear with me on this one, but Vic Kostuik asks, why does a mirror only reverse the image in the horizontal plane and not in the vertical?
Now, that's a really great question that always gets people confused. And the answer is actually surprisingly simple. That when you look in the mirror, nothing is actually inverted at all. Because if you look to your left in the mirror, you see your left side, and if you look to the right, you see your right side. But it is different from what people see when they're in front of you and they turn around to look at you. And the reason why that is because they're actually turning around to look at you in the process of turning around. Things that were on their left are now on their right, and vice versa. So they have flipped left and right by turning around. But a good thought is there's another way that you could turn around to look at something, and that's the heels and stand on your head. And then not inverted at all, but up and down inverted.
And you may have been wondering what we were doing asking that question in Naked Astronomy, but here's the second part of the question. He said, if you have a mirror in space, on what plane would that reverse the image?
Well, in a space telescope, the effect would be exactly the same. It's the same in space as on Earth, and the image would not be inverted at all.
That was Dominic Ford with Andrew Bonson and Carolyn Crawford discussing your space science questions. If you've got something for Santa to tackle, then just get in touch by email to astronomy@thenakedscientists.com. But that's all we have for this Naked Astronomy podcast. We'll be back soon with more space science news, interviews, and your questions. If you'd like to subscribe to Naked Astronomy, you can search for us on iTunes, or you can join us at thenakedscientists.com/astronomy. Naked Astronomy is produced by me, Ben Balsler from The Naked Scientists, and it comes to you from Cambridge University with support from its eccentric university team and the Science and Technology Research Council.
There's always a choice. You can choose the chaos of outdated technology, fuel uncertainty and being over a barrel. Or you can choose Polestar, 100% electric. See in the financial year offers at polestar.com.
There's a lot of potential for your membership. You can save time with online telehealth appointments, or save money with NIB's no-gap extras. And you can save both with NIB's easy in-app claiming. It's not just good, it's potentially amazing. Which is probably why we've just been We Money's Digital Health Insurer of the Year for 2025. TNC's apply, visit nib.com.au today. Thrust in space science into the audio dimension. This is Naked Astronomy.
On the Naked Astronomy podcast this month, cosmic climate change, we find out why the universe went through a warming period, and what would aliens see if they were looking for us.
Right, so probably the most notable feature that you would see if you were looking at our solar system from afar is this large circumsolar ring structure that goes all the way around the sun and has a radius approximately equal to the distance from the sun to Neptune.
We'll find out how Neptune draws a dusty ring around the sun later on. Plus, news of asteroid structure flying through Venus's atmosphere at the end of the day. I'm Ben Balsler from The Naked Scientists, and this is Naked Astronomy.
Support
Supported by the STFC and Cambridge University's 800th anniversary team, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
Let's start by joining our expert panel to catch up with the latest news in astronomy and cosmology. Andrew Bonson, Dominic Ford and Karen Crawford joined me in the studio.
Well, I've been looking at some images that have been released from the mid-July flyby of asteroid Lutetia by the Rosetta spacecraft. Now, these are interesting because there are lots of asteroids out there, but we don't actually know that much about them. We can study them from the ground, but it makes a lot more sense if you can go close to one and actually examine it in detail. And Rosetta is a spacecraft that's slowly winging its way to the outer solar system, where it's going to rendezvous with the comet in 2014. But en route, it's swung by this, it's quite a giant asteroid. It's 21 Lutetia, which means it was the 21st discovered back in 1852. And as it approached the asteroid, it had all the imaging and spectroscopy instruments switched on, and these work in a range of wavebands, so it's not just optical, but a lot of near-infrared imaging and spectroscopy. And the idea was just to study the structure and appearance of the asteroid. Now, this thing's quite elongated, longest dimension about 130 kilometres, and they've just released some fabulous pictures of the surface, and you can see craters all over the surface. You can see boulders, you can see scarp slopes, you can see evidence for landslips. It's a fascinating landscape, and in particular, everything is really covered by this deep blanket of impact debris called regolith. This is the kind of dust that covers the moon. Because this asteroid's big enough, it's got enough gravity that if an impact happens on the surface, all the material then settle back down to the asteroid, and it just piles up and forms this covering all over the surface of the asteroid. I mean, obviously, this is just an initial release of the picture. They're still analysing lots of the data. But one of the preliminary results is actually measure the density of the asteroid to find out more about what materials it's made of. And it's not dissimilar from the Earth. It's less. It's about 3.5 grams per centimetre cubed. So substantial rocky component, obviously, to the asteroid. Specifically, what minerals are in the surface will come out of the data with the infrared spectroscopy. That's going to help us place how asteroids form and evolve in the solar system, how they fit into various scenarios for the formation of the planets and the different groups of planets, as well as help us understand them better if one should ever come close to them and present an impact risk.
Rosetta's been a fantastically useful mission so far. It seems to have had a lot of opportunity to pick up data on its way to its actual target.
Well, it is fantastic that it's able to do that, given it's spending so long getting to its target. You might as well miss the journey.
Thank you very much. And Dominic, what news do you have for us?
Well, this is quite a neat experiment which the European Space Agency have been conducting with the Venus Express spacecraft. And the question is, how thick exactly is Venus's atmosphere? Now, we know how thick the atmosphere is on the surface because we've been there. In the 1970s, the Russians landed several spacecraft on Venus's surface. But we don't know that much about the upper atmosphere. And so what the European Space Agency have been doing is they've manoeuvred the Venus Express spacecraft into orbits that swoop down into the atmosphere. And they've been measuring the friction that the spacecraft feels as it swoops through the atmosphere for about 6 minutes at a time. And the way that they measure that is they've turned the spacecraft solar panels so that one of them is edge-on to the atmosphere and the other one is face-on. So on one side it has lots of friction with the face-on solar panel, and the other one has very little friction. As the spacecraft moves through the atmosphere, it twists because of the friction. And at the end they can measure how much that twist is, and from that they can work out how much friction there was. Now, at the moment they're being quite cautious. They're doing these swoops at quite high altitude, where they think the atmosphere is quite thin. And once they've shown that the atmosphere at those altitudes is not so dense that it might actually rip the spacecraft apart, they're going to start swoops at lower altitude and then start getting a profile of the density of the atmosphere with height. And that could really help us to understand the weather systems that we see on Venus.
You say at relatively high altitude. Comparing it to Earth, how high above the surface are we looking at?
So the swoops so far have been at an altitude of about 175 kilometres. And to give you an idea, we tend to talk about the boundary of space being 100 kilometres above the Earth, so this is very high altitude.
Thank you, Dominic. Andrew, we've had some observational evidence of some unusual-looking very old galaxies.
That's right. There's been an announcement this month by an Italian group led by Giovanni Cresci about some observations they've been taking with ESA's Very Large Telescope. That's the sort of flagship telescope located in Chile. And these particular observations are taken with an instrument known as SYMPHONY, and that's what we call an integral field spectrograph, which means that not only is it taking an image of the galaxies that they're looking at, but at each point in that image it's actually getting a spectrum. It's sort of decomposing the light into all its different colours, so they're getting an awful lot of information in one shot, if you like. So to explain why they were looking at these particular very ancient galaxies, we have to ask, how is it that galaxies grow? Because we know that galaxies have got bigger over the age of the universe, from small tiny seeds to the 100 billion times the sun monsters that form today's galaxy populations. And how exactly that process happens is still somewhat up for debate. We know that mergers are important, so two small galaxies can literally merge together and become one larger galaxy. But also, theoretical evidence has been pointing recently towards the importance of what we call cold flows. And that's when there's a sort of continuous flow of cold gas from outer space into a galaxy. The interesting thing about cold flows is that even though our simulations are theoretical evidence suggests they could be very important, observational evidence for them, actual direct observations that tell us they're happening, have been pretty hard to come by. And that's what the announcement this month has been about. The claim is that they're seeing evidence for these cold flows. And the evidence that they claim they're seeing is that the centre of the galaxies that they're seeing, the centre of these young galaxies, have very little what we call metal enrichment. The composition of the gas is very close to the primordial composition of gas after the Big Bang, whereas the outer reaches of the galaxies have quite a lot of metal enrichment. In other words, there's been a lot of stars formed. Those stars have exploded in supernovae and put out a lot of heavy elements into the gas. And that means that what they're seeing is very little heavy elements in the centre of the galaxy and a lot of heavy elements at the edge, and they're interpreting that as meaning there's cold gas essentially pouring into the centre of this galaxy. Now, it's certainly a fascinating observation, but I'm not sure I totally agree with their interpretation of this, because having worked on some of these simulations, what you actually see is that these cold flows deposit pristine gas onto the outer edges of the galaxy rather than the centre of the galaxy. So that should mean that the outer edges of the galaxy are more pristine than the centre, exactly the opposite, in fact, of what they're seeing. So it's certainly fascinating to see this effect, but I don't think we actually understand it yet.
Just to clarify, in astronomical terms, when you say heavier elements, you're not talking the same way that a chemist would mean a heavy element. You just mean things that are heavier than hydrogen or helium.
Yes, so that's absolutely right. Anything heavier than helium essentially wasn't produced in the Big Bang, and so it's happened later inside galaxies.
We can go ahead and clear this up and clarify what is actually going on. I assume we can't observe gas itself because it's cold and probably not that dense.
Well, there are two things that we have to do. First of all, we have to do more observations like this. We have to do more observations like this to see whether it's just an unusual blip. But secondly, actually, we can see gas, even though when it's very distant. We do this through a technique known as absorption line spectroscopy. So there are opportunities to actually see these inflows of gas directly, which makes it even more surprising that we haven't seen them to date. So there's clearly something that's not really adding up here, and it's going to be interesting to keep an eye on it.
Thank you, Andrew. That'll be interesting to see what happens in the future. Carolyn, back to you.
I wanted to mention a discovery of a cluster of galaxies. Now, we have plenty of clusters of galaxies in the nearby universe. These are gravitationally bound collections of hundreds to thousands of galaxies, all confined within about a few tens of millions of light years around region. And it's not just the galaxies, there's hot gas there, there's dark matter there, it's all held together by the neutral gravity. Now, we've seen many such structures in the local universe. And what's interesting is that the history of formation of such structures can provide very strong constraints and different ontologies. How do you grow such clusters as the universe ages? And one of the key observations that can help this is finding early versions of these clusters. And as someone who has spent part of her own research career looking for high redshift clusters of galaxies, I'm very delighted to tell you about this cluster because it is enormous. It's got the mass of 800 trillion of suns, hundreds of galaxies, and it's a redshift of over 1, which means that it dates from when the universe was only about half its current age. It's 70 billion light years away from us. The exciting thing about this is, obviously we're seeing as it was 7 billion years ago. If we could see it as it is now, it would be about the largest gravitationally bound structure in the whole universe, but obviously we're seeing it as a snapshot in its history. And actually when you look at the galaxies within it, they're quite large and quite well evolved, which means that they've existed for at least a couple of million years already. So this is telling us that this enormous structure, a redshift of 1, got its act together much earlier on in the universe than perhaps we were expecting, and it starts to provide a very interesting constraint on how and when formation of structures happens in our universe. The other interesting thing about it is that this cluster was discovered with the South Pole detector. This works in the millimetre wave bands. And it was detected by a technique called the Sunyaev-Zelkovich effect. And this is where a cluster of galaxies at any redshift away from us can produce a minuscule distortion in the background light of the cosmic microwave background. And they are surveying the skies. It'll be interesting to see how many of these high redshift clusters they find. It's just very interesting that they produced one really massive one already.
Thank you, Carolyn. Dominic, back to you.
A paper published in the Astrophysical Journal this month has announced the first ever discovery of a supernova in the infrared waveband. Now, supernovae, of course, are massive explosions which occur at the end of the lives of high-mass stars, and they are incredibly bright. For a short period, these stars become tens of billions of times brighter than our sun, and they often become brighter than the entire galaxies that they live in. Now, there's something slightly surprising about these supernovae, which is that although you might think they'd be quite conspicuous being so incredibly bright, in fact, we think a lot of supernovae go completely unobserved. For example, we think in our own Milky Way galaxy, supernovae go off about every 50 years or so, yet the last supernova actually to have been seen was over 400 years ago in 1604. The reason why we think that is that you can see supernovae both in the radio and in the optical. And in the radio, you see a huge number of expanding remnants left over by supernovae, yet no one has ever seen the supernovae which caused these remnants. Now, we think the reason why these supernovae are being hidden from our view is that galaxies are pervaded by solid gritty particles that we call dust, and this just simply obscures the light from our view. But if this dust is obscuring one of these supernovae, you would expect them to be heating up this dust. This energy's got to go somewhere, and so you would expect to see a thermal emission from this dust, yet no one's ever seen that before. And in this paper, the Spitzer Space Telescope was making observations of a large area of the sky at 7 different epochs and looking for sources which appeared or disappeared. And in this case, it picked up a source which appeared and stayed there for about 6 months and then faded away. And if you've done the calculations, they think the dust in this galaxy is to a temperature of about 300 degrees. If you work out how much energy it would take to heat up that much dust to that temperature for 6 months, it's about the energy release of a supernova. And it's very hard to see any mechanism that could have warmed that dust. So this is a pretty good candidate for an obscured supernovae, which no one saw in the optical.
Are we getting any better at predicting supernovae? Can we use any models to actually work out where we should be looking to try and catch them in the air?
Supernovae tend to occur most often in heavily star-forming galaxies where you've got large young populations of very massive stars. And these galaxies actually tend to be more dusty than other galaxies. And so you have less chance to actually see the supernovae. And that's why it's so interesting to be able to see them in the infrared.
So there's clearly an awful lot that we need to concentrate our observations on. Why are supernovae so interesting?
The supernovae are massively important in the evolution of galaxies. They're actually the source of most of the heavy elements, which Andrew was talking about just now, in galaxies. And they also stir up the interstellar medium and actually cause a lot of star formation.
Thank you very much. Andrew, if we can come back to you for one last story, and this one is about the end of the WMAP. Now, first of all, just explain what WMAP is.
Well, WMAP is NASA's current mission to measure the cosmic microwave background. That's the afterglow of the Big Bang itself. And we've discussed it briefly on the podcast earlier this year, because earlier this year they released the 7-year results. That was the results from 7 years of observation, showing in better detail than ever before exactly what the patterns in this primeval radiation look like. And this month, NASA have announced that they finished operations with the WMAP satellite. So they collected 9 years' worth of data. The extra 2 years are still being analysed, so it will be a while before we actually see the 9-year results. But in terms of the hardware, that's now being decommissioned. Now, that's not too sad, because although WMAP has really changed our picture of the universe, and it's hard to understate just how revolutionary its results were at first. I think I mentioned earlier in the year that the 7-year results didn't really add much to what we had before, and we don't really expect the 9-year results to do anything particularly new either. So it's a law of diminishing returns here. And of course, ESA have launched the Planck satellite, which is the natural successor to WMAP, and so we hope to be getting some results from Planck early next year, and then a really exciting cosmology results from Planck probably sometime in 2012.
And hopefully we'll be here to report on those findings too. That was Andrew Hobson, and before him, Karen Crawford and Dominic Ford, with a roundup of space science news. They'll be back later on to tackle your questions.
Expand your mind and then tune in. Naked Astronomy, the stellar space science show. For more episodes of this program, look us up online at nakedscientist.com/astronomy.
Still to come, we explore the climatological history of the universe. But first, we've reported on the discovery of exoplanets before on Naked Astronomy, but what would our solar system look like to extrasolar observers? Dr. Chris Stark from the Carnegie Institute in Washington has been trying to find out.
Well, if we go back to sort of the beginning of the story, many people think of space as a vacuum. In fact, in our solar system, it's not quite a vacuum. There happens to be a lot of dust in our solar system. And especially near the Earth, we've detected this dust. We can actually image this dust through its light that it reflects from the sun. Or if we look in infrared, it's actually very bright. And the dust near Earth, we call the zodiacal cloud. And in fact, you can see it with your naked eyes at night. If you look near the horizon, it sort of looks like a wedge-shaped glow in the sky. And we think that this dust that occurs near Earth is actually created in the asteroid belt and due to comets that are whizzing past the sun. And what we think is basically asteroids are colliding and producing this dust, and comets are sublimating. But we know that there's another reservoir of bodies in our solar system near the outer regions, near the orbit of Pluto. And that reservoir we call the Kuiper Belt disk. The logical conclusion is essentially that we would think that the Kuiper Belt objects, similar to how the asteroid belt is behaving, would also be colliding and producing lots of small dust grains. And although we haven't directly imaged the dust from the Kuiper Belt, because it's much more difficult to image than the dust that's near Earth, because essentially we would have to look through all of the dust near Pluto before we can image the dust produced in the outer regions near Pluto. There have been a couple of missions that have flown into the outer regions of the solar system with a dust counter on board. And so we have a rough idea that dust exists out there and how much dust there is. And in fact, we believe that there's so much dust that if you were to image our solar system from afar, that dust would be one of the most easily imaged features of our solar system, especially if you look at infrared. So the problem is we know there's a lot of dust produced in the Kuiper Belt, but we really have no idea what it looks like. And so if we want to sort of explore what our solar system might look like to an extrasolar observer, we have to rely on theory then to sort of infer what the dust from the Kuiper Belt would look like.
And what does that entail?
That's where I come in. Recently, Mark Kushner and I have produced some new models that predict what this dust distribution might look like. These theoretical models that are produced have to include certain dynamical effects. The dust grains are perturbed, their orbits are changed by the gravitational influence of planets, and if there's enough dust, actually two dust grains can collide with one another. And so if you want to produce a model of the Kuiper Belt dust disk that includes both gravitational interaction with planets and collisions between dust grains, then you have to do what we call an n-body integration. The problem that people thought was very daunting was that there are so many dust particles in our Kuiper Belt, on the order of 10 to the 20th or up to the 30th dust grains, that people thought there was just simply no way to do this with current computational capabilities. For example, the most intense n-body integration so far has been maybe 10 to the 6th particles. So we're talking orders of magnitude more particles than what we're currently capable of. And so to produce a model that includes both collisions between dust grains and the gravitational dynamics that's necessary is very, very challenging. Fortunately, Mark Kushner and I came up with a tool that essentially allows us to accomplish this task. And we call that tool essentially a collisional grooming algorithm. And basically what we do before collisions been included in the first place. And so what we're able to do is, for the first time, we're able to produce a model of our Kuiper-Belt dust cloud that includes both gravitational dynamics as well as collisions between dust grains.
So what's the distribution of dust in our solar system actually like? Is it fairly homogeneous, or do we get bands, do we get clumps? What would we expect to see if we were actually an extrasolar species looking down onto our solar system?
Right, so probably the most notable feature that you would see if you were looking at our solar system from afar is what we call a resonant ring structure that Neptune ends up creating within the Kuiper-Belt dust cloud. Basically, Neptune selectively places dust grains into specific orbits, which we call mean motion resonant orbits. And what this does is it creates this large circumsolar ring structure that goes all the way around the sun, and it has a radius approximately equal to the distance from the sun to Neptune. And it also creates a gap within that ring. And so if you were an extrasolar observer looking at our solar system, one of the first things you would notice is that resonant ring. And the gap in the resonant ring would tell you essentially where Neptune was, and exactly the mass of Neptune, even if Neptune was too dim to directly see itself.
So could this in principle be used to look for extrasolar planets, where perhaps some of the other technique or we just need an extra technique to confirm what we're seeing from, say, gravitational wobble?
Exactly, yes. We think that in the future, when our technology improves slightly, we'll be able to see these sorts of resonant rings for ourselves. And we do expect to see rings produced that have gaps, and maybe we can pick out the planet within those rings. In fact, we have seen some rings that are very similar to what we predict, although they are in much more massive systems, and so the dynamics are slightly different in the systems. We have detected rings in other systems that have gaps and clumps and all sorts of interesting features, but so far it's been difficult to determine what this implies about the planets that are in that system.
And of course, the universe is actually quite a dusty place, so there must be quite a lot of dust for you to observe and quite a lot of dust to model.
Yes, in fact, a surprisingly large fraction of stars exhibit dusty disks around them, and so we think we're going to be seeing or imaging lots of disks and seeing hopefully lots of these ring structures that planets are creating.
Now, this is at a modelling stage, but you can use your results to inform what observations people should be making. What do you need to see out there in reality now in order to make your model a bit better?
It would be nice to confirm the existence of specifically Neptune's ring structure that we predict. To make those observations, it's very, very difficult because, as I mentioned, to see the dust out near the orbit of Neptune, you have to look through all of the dust in our solar system before you can see it. And so something that we've suggested that may work is, instead of trying to just detect an image of the dust, look for essentially an alternating or a varying image. In other words, look for the asymmetries that we predict and looking for those as they move.
One of the advantages with modelling is that you can roll it forwards in time, you can roll it back in time and make predictions based on your model. Do we think the solar system has essentially always looked like this?
In fact, no. We think it has changed quite a bit. In the past, the Kuiper-Belt was much more massive, and essentially we think that it has been collision eroded over time. So in the past, this means that it was more massive, there was more dust, and this means that collisions between dust grains happen more frequently. And so what we're able to do is essentially tune our model and look at what the dust distribution may have looked like billions of years ago. And what we found was actually very surprising. It turns out that one of the first things that happens when you go back in time to a more massive disk is that Neptune's resonant ring structure disappears. If you're an extrasolar observer looking at our solar system when it was very young, you would not see this circumsolar ring with a gap near the location of Neptune. That would just be missing. Instead, what you would see is you'd see a very circularly symmetric ring that is basically just tracing the location and the distribution of the Kuiper-Belt objects that are colliding to produce the dust. Basically, Neptune's gravitational imprint disappears.
And so what's the next stage for you? What's the next step in your research?
Astronomers have already detected ring structures around other stars, but all of these ring structures that have been detected so far are around very young stars. It means that we're not necessarily seeing the gravitational imprint or the resonant ring structure that I described earlier. Instead, what you're seeing is essentially the dust is tracing the distribution of parent bodies. So one of the things we're interested in is trying to model observed ring structures around other stars and seeing what we can learn about the distribution of parent bodies in those systems.
Chris Stark explaining how Neptune carves a distinctive ring out of the cloud of dust that pervades the solar system. Now, it's not just the climatologists who concern themselves with looking at how temperatures have changed throughout history. George Becker, a fellow at the Kavli Institute for Cosmology, has been looking much, much further afield and discovered warming on a cosmic scale.
The broad question is really broad. It's how do galaxies form in the universe? And then how do these other things sort of materialize in the wash of gas and dark matter that we live in? If you look up at the night sky, or if you look at a very deep astronomical image, what you see are galaxies. And you see other things, these things called quasars, which are these black holes that are swallowing up material and shining very brightly. That's what you see, but that's not all that's out there. What fills most of the universe is this very, very thin network of dark matter and gas that we call the intergalactic medium. And if you were able to see it, it would look like a cobweb or like a sponge. And what we believe is that over time, the small variations that were present right after the Big Bang gave rise over time, by the way they collapsed through gravity, to this network of material, and within that network, galaxies. So this is a system that comprises all the matter in the universe, and how which galaxies form. And it's dynamic. It changes with time. One of the things that happens is that it goes from being neutral electronically neutral to being ionized. Neutral means that it's similar to the gas that's in the air in this room. The gas is made up of atoms, and those atoms have electrons, and the electrons are attached. And that's true for most of the matter on Earth. But as you go out into space, that changes, and especially as you go out into the regions between galaxies. If you find an atom, and they're a little bit more rare out in space, but if you find an atom, chances are very good it won't have its electron attached. It will have been knocked off a long time ago by some energetic photon. That photon probably came from a star, or it came from a quasar, traveled through space, found an atom, and knocked off the electron. And that's the way the universe is today. It's spread out in this network of material that is very, very highly ionized. And the question I'm addressing is, how did it become that way? How did the ionization happen?
I guess that because we know that in order to become ionized, they've had to interact with photons at some point, we can sort of use the ions themselves to get an idea of the history of the universe.
Yeah, that's exactly right. If you knew how this ionization process happened, then you would know when it was, for example, that galaxies had gotten far enough along, enough had formed to produce enough photons to do the job. Similarly, quasars are also important in this mix, because it turns out that all this gas that's out there is primarily one of two elements. It's either hydrogen, and hydrogen is far and away the more abundant part of this gas. And then there's also helium, just like in the sun. It's mostly hydrogen, helium, it's mostly hydrogen, helium, and then just a few other trace elements. We believe that galaxies are responsible for ionizing the hydrogen, but it takes quasars to ionize the helium. And the reason for that is that helium atoms have 2 protons, and they're just a little bit better at holding on to their electrons, and you need higher energy photons, enough of them to knock those electrons off. So we believe that it was quasars that ionized the helium, and that's actually the stage of this ionization process that I was looking at.
I assume we can't directly observe these fairly rare ions themselves, and instead we have to use light coming from distant sources. And you're looking at quasars, but how can you actually do that? What observations do you need to make?
That's right, the quasars are playing 2 roles here. Number 1, they're providing the photons that we think is important for the physics, and number 2, they're serving as background sources of light that we observe with large telescopes on the ground. So most of the observations that were done with the Keck telescopes that are on Mauna Kea in Hawaii, these are 10 wide diameter mirrors. Other observations were made with Magellan telescopes in Chile, which are also large optical telescopes. So what we do is we look at these quasars. The light from the quasars has traveled through the intergalactic medium, all this gas, and the gas has absorbed part of the light from those objects. In fact, every time the light goes through a cloud of gas, it loses a few photons. And so by the time it reaches us, it reads like a ticker tape, or like barcode. And the information about where the gas is and what it's made of is all encoded in the quasar light itself. So that's what we're observing and trying to make sense out of when we observe the telescope.
That must be quite a difficult task. For example, how do you tell the difference between a cloud of gas that's a very long way away but very large, or one that's quite close to you but quite small?
The universe does us a great favor here by expanding. When the photons were emitted, that was a long time ago, and the universe was much, much more crowded in the sense that any 2 points were just a lot closer together than they are today. So you have to imagine the quasar lives, gives off some photons, and those photons begin to travel towards us. And along the way, the universe expands and expands. The photons also expand, because they don't have any mass to hold themselves together. Only when the photon is a very special length or a very special frequency that they can be absorbed, that they will come to a cloud of gas and get absorbed by it. And so each cloud of gas gets to absorb only a very specific part of the quasar spectrum. There's a very special part of the light that was originally emitted by the quasar. And so the expansion of the universe sort of stretches out the quasar and allows us to read off by the wavelength that we observe from the ground where it was, or rather by how much the universe had stretched out by the time the photon had been absorbed. It all sounds a little bit convoluted, but the end result is that we get the light from the quasar, and there are a series of absorption features that we can read off. And the redder an absorption feature is, the further back it was absorbed.
So, using this technique, reading the quasar barcode, what have you been able to learn about the universe?
Well, it goes back to this ionization question. How did all this ionization happen? In fact, we call it re-ionization, because at the very beginning, right after the Big Bang, all this gas would have been ionized because the universe was very hot. The universe expanded, it would have cooled down, and these electrons would have found their atoms and recombined, and the gas would have been neutral. And so the ionization that's done by galaxies and quasars is the second ionization, which we call re-ionization. Along with actually doing the ionization, that is knocking the electrons off, re-ionization should heat up the universe quite a bit. And the reason for that is that when one of these photons hits an atom and knocks the electron off, it's got more than enough energy to do that. And the extra energy gets carried away by the electron, and the electron shares that extra energy with the gas around it. And so once all this ionization is done, and these electrons which have a little bit extra energy go flying around, the gas gets quite a bit warmer. That's the signature that we were looking for. What that means to the quasar spectrum, this pattern of absorption features that we read off, is that they tend to look a little bit smoothed out. The gas itself puffs up a little bit as it gets warmer, and that smooths out these absorption features. And the fact that the gas is hot also creates a smoothing in the appearance of the absorption features. So that's the signature that we're looking for from the quasar light. We make a comparison to numerical simulations that we can run, where we change the temperature by hand, and we get a match. That is, when we have a simulation, gas temperature that sort of reproduces fake quasar spectra that appear start way back in the Big Bang would have been extremely hot. We're talking millions of degrees, but shortly after the Big Bang, things actually do get quite cold. The universe will get down to just a few tens or maybe a few hundreds. I'm talking about sort of the temperature of an average piece of gas in the universe. Then when the first galaxies light up, we don't know, because we haven't been able to measure temperatures that far. What we believe is that when galaxies light up and the ionization of hydrogen happens, they will get somewhere up to the range of, say, 20,000 Kelvin. It might be considerably higher or a bit lower. Then the universe will start to cool down again until this helium ionization, what we were looking at, occurs. And there, the theoretical expectation was that you'd get a boost again, say another 10,000 Kelvin. So you might have cooled down to 10,000 Kelvin, which sounds hot. It's hotter than the surface of the sun, and up to say 20,000 Kelvin. And after that, the universe starts to cool down again because it doesn't have this source of helium any longer. And then sort of strange things start to happen in the very recent past, where these sheets of gas that are collapsing start to shock and heat in very interesting ways. But that's a different process.
So just looking at this ionized gas, it really infer quite a lot about galaxy formation, about galaxy progression, and not just about the history of the gas itself.
We're right at the beginning of being able to make those kinds of inferences. This process with helium really involves the quasars. The quasars live in galaxies, and we know that the formation of quasars, which are black holes again, that are swallowing up material at the insides of galaxies and giving off tremendous amounts of radiation. Those black holes are intimately connected with the development of the galaxies. They reside in them somehow. So putting together how quasars form, how black holes form, how galaxies interact with their surroundings, this form of the intergalactic medium, it's all part of getting the complete picture right. It's all part of understanding how galaxies form and how the universe gets to be the way it is. The next step is not only to understand helium ionization, which happens somewhere between, say, 1 and a few billion years after the Big Bang, is to push further back in time and to really start to understand hydrogen ionization. And that's getting into pretty murky territory. And that involves the formation of the first stars, the first galaxies, things about which we're just beginning to learn the basics and understand ionization. It's going to get us a long way there.
George Becker from the Hadley Institute for Cosmology here in Cambridge, explaining how understanding reionization can help to fill in the gaps in the history of the universe. This is Naked Astronomy, the space science podcast from The Naked Scientists. If you've got any questions or comments for us, get in touch by email to astronomy@thenakedscientists.com. But now we return to Carolyn, Andrew and Dominic to take on your space science questions. First of all, Dave Johnson wants to know where the best place to site a space elevator would be.
One just science fiction idea for a more efficient way to get things up into space and back down again. And it essentially consists of an orbiting space station which has a very large pulley on it. And you thread an enormous cable over your large pulley and put a lift on one side of it and a weight on the other side. And then if you imagine as you turn this pulley, the lift comes up and the weight goes down. That means with very little energy expended, you can actually lift things off the surface of the planet and into space. Now, the key point, if you really wanted to do this, is that you don't want the space station to move relative to the ground, otherwise the lift will be swinging all over the place. It would be almost impossible to get safely into space. So that really restricts your options, and in fact, you more or less have to go for a circular orbit, which is what we call geosynchronous, and that just means it moves with the ground. And that tells you have to be about 36,000 kilometers above sea level over the equator. So if you wanted to build a ground station for one of these things in preparation for the coming of the sky elevator, choose somewhere that's exactly on the equator.
In Dave's question, he specifically suggests that we try and put it somewhere very high up, like on the peak of Mount Kilimanjaro. Would that extra elevation actually make any difference with that?
It wouldn't really help you a great deal because, as I said, you have to be the space station that's pulling you up is 36,000 kilometers above the surface. And if you compare that to something like Mount Everest, that's just 9 kilometers tall. So you are only shortening your journey from 36,000 kilometers to 35,991 kilometers, not making a great deal of difference.
And of course it means that you have fewer sites that are actually on the equator. I don't know if there are any mountain peaks directly on the equator. Anyone know?
My geography is not good enough.
And it would also be a lot easier to build your base station on the ground rather than carting everything up to the top of the mountain. So I think we'll go with Andrew's idea.
Carolyn, you were talking about observing asteroids earlier. We've had a question from Adrian. They say that we know the Earth has been hit by asteroids many times in the past, and it has resulted in mass extinctions. So what's the likelihood of being hit by an asteroid in our lifetime?
So going up in an elevator to coming down with an asteroid, yes. We know certainly there have been asteroid impacts in the past. There are craters over the surface of the Earth, craters down the sea that get eroded by the wind and the sea. We have evidence of a massive extinction caused by an impact that we think was 10 kilometres across about 65 million years ago, and that's impacting at 20 kilometres per second, and this formed the Chicxulub crater, and it's responsible for wiping out the dinosaurs. And the most recent event we know about happened just over 100 years ago, 1908, Tunguska, where something didn't even survive the fall through the atmosphere, but exploded above the ground, flattening over 80 million trees over a diameter of 2,000 kilometres squared. So, yes, we are vulnerable to impacts. The thing to realise is the probability of a really major impact is quite
sorry,
it's the smallest near-Earth objects that we call them. So think
poetry
possible.
possible.
Pass the Earth fairly regularly. In fact,
Yeah,
this month,
doing a workout.
there was an
I'm
object
surprised you
about
didn't comments didn't
5
come up on
meters across that flew about 46,000
over here.
kilometres above East
Look
Asia.
at What's going on here?
And such things that tend to cross are not that dangerous. We expect that even if they fell onto the Earth, they would completely disintegrate in the atmosphere. You've got to be worried about things that are more like a kilometre in diameter, and we reckon one of those comes close to the Earth for every 200 to 300,000 years. So that's longer than modern humans have been around. Now, if one of those landed,
sorry, I only had
just on a more local, global catastrophe, you're looking at something that's more like 10 kilometres across. This is like the Chicxulub event. And we reckon we're threatened by one of those about every 100 million years ago. So I know we're only talking probabilities, but if that was an accurate assessment, you could guess that we're probably not in great danger yet. I mean, whether something's dangerous doesn't just depend on how big it is and therefore how much mass it's got. An important factor is what speed it's moving at. So the amount of energy released is just your old half mv squared, your kinetic energy, and the speed is really important. These things impact at 20, 30 kilometres per second. We reckon there are about 2,000 near-Earth objects out there, perhaps only about 400 of these that we know about that are potentially damaging. And there are programs all over the world where we're continually monitoring such objects. And the idea is that you know their orbits, their speeds, their sizes.
Sorry,
and
poster
we can
imposter.
isolate anything that might be a serious threat.
I missed your messages. I had this set up the wrong way, so
strategy to counter the potential damage caused by an impact.
I want to see.
So no need to start buying asteroid impact insurance just yet.
No, but good need to continue funding monitoring programs that map the stars.
Thank you, Caroline. Dominic, thinking of things falling down to earth, we've had a question from Roger Malarkey.
Sorry, for some reason.
Space station obviously need supplies occasionally, and they're delivered by things called progress modules, which then burn up in the Earth's atmosphere. Can we observe them coming?
Just doing upper body workout today. Sorry, I thought I've got the other iPad over there monitoring the stream, but I guess I had it in the wrong settings because your comments didn't show up. So I hope I fixed that now. Hope your comments start coming back up in front of me. Oh yeah, just doing an upper body workout today. Combination of push, pull, and back. Really.
And so these are quite big lumps of metal. And yes, they do produce tremendously bright fireballs when they come into the atmosphere. However, you don't see many pictures of these things burning up. And there's a reason for that. Because these large spacecraft may actually make it through the atmosphere. You may get some shards of metal reaching the surface. And obviously, in an inhabited area, that could cause injury. But to make sure that doesn't happen, all of these re-entries are over the Pacific Ocean, where you've got a vast expanse of uninhabited area. And they also aim away from regular shipping routes, where trips aren't affected. So I had a look on the internet. I found, I think, one image that someone had taken of the Pacific Ocean. But for the most part, these tremendous celestial events go completely unseen.
Andrew, this is a slightly new question. It's come in on Twitter from Robotaholic. And he wants to know if information can be coded into gravity waves. And if so, should we be looking for those codes?
Well, the simple answer is yes. I mean, very much like other waves, you can code information into gravity waves. Now, we're more used to coding information into things like electromagnetic waves. That's what you or I would call radio waves, for instance, which carry signals like radio, television, mobile phones, and so on. And light, in fact, is an example of an electromagnetic wave, and obviously that can carry information as well. And those kind of waves are caused by taking a charged particle like an electron and accelerating it in one way system to wave the particle around, and that creates the electromagnetic wave, and off it goes. Now, gravitational waves, which are predicted by Einstein's theory of gravity, known as general relativity, are similarly caused by accelerations, but they're caused by accelerating any body with mass. So
I don't know what's wrong. Your comments aren't showing up on your comments aren't showing up on my iPad. Sorry about that.
But the trouble is, they're extremely hard to detect directly. We do have
I wonder why they're not coming up here.
that Einstein's theory is right in this regard, and some of the famous examples are from looking carefully at pulsars. In fact, Hulse and Taylor, who discovered the Hulse-Taylor pulsar, were awarded the Nobel Prize for their work on this, and it's to do with pulsars which are orbiting other stars, and the particular way they radiate out gravity waves makes the rate at which the pulsars spin change, and we can detect that and so on. But we're not directly detecting the gravitational waves, just the effects.
For some reason, the chat's not coming
If you
up.
wanted to directly detect gravitational waves, you're looking for a very subtle oscillating deformation of space. It's like space is squeezed and stretched in sort of alternating cycles. And that's a very subtle effect. There are, in fact, instruments looking for this. One example is the Laser Interferometer Gravitational Wave Observatory, LIGO, which has a laser which points essentially into a 4-kilometre tube, and then at the other end a mirror, so that using a technique known as interferometry, they can tell whether the length of that tube is changing just because of gravitational waves. But so far, no gravitational wave has been detected directly, just because technologically it's so challenging. And it would be technologically a billion times harder to actually send out a gravitational wave. All these gravitational waves come from extreme events out there in space, like things involving pulsars, which are very rapidly rotating neutron stars, very exotic objects. And so, although it starts with this very everyday story of just moving particles around, to actually get something measurable, you need such incredible technological prowess. It's very hard to imagine any alien civilization really bothering when they could just send us a radio wave.
So not really the right place to be looking for alien messages just yet. Carolyn, we've had a question from Damien Huxley. Now, we've mentioned Hawking radiation before when talking about black holes. He just wants a bit of clarification on what it is and how it actually acts with tiny black holes.
Okay, well, let's just start with the idea of a tiny black hole, or a mini black hole that they're often called, because these in themselves are an interesting concept. The kind of black holes we study and we know about in our galaxy are formed, say, from the collapse of very massive stars, and only very massive stars have enough self-gravity to completely collapse and form a black hole. If you get a star the size of our sun, the mass of our sun, or up to 20 times the mass of our sun, when it reaches the end of its life, it doesn't have enough self-gravity to collapse into a black hole. So the only way you get a mini or a tiny black hole is if you could squeeze it from the outside and apply enough force to push it down so that it becomes concentrated enough. And it's arguable whether we can ever do that. There are ideas that certainly those invented by Stephen Hawking in the 1970s that perhaps during the Big Bang there were such enormously strong forces around that these could squeeze matter down to form mini black holes. And here we're talking like the mass of a mountain squeezed down into a proton. I want to stress that this is a completely theoretical idea, yet there's no observational evidence for these. If they were formed, they could be distributed throughout the universe. But the catch is that even if you have a mini black hole, you don't necessarily expect it to last very long due to Hawking radiation. This is quite
There we go.
I'm just trying to simplify.
What's wrong?
If you have the vacuum of space, it's not completely
Poster imposter. Sorry. For some reason,
being created and annihilating each other all the time, popping in and out of existence. Now imagine
for some reason, I couldn't see your.
If you have one occurring right near the event horizon of a black hole,
I couldn't see your comments.
one of those particles to fall into the black hole.
So I don't know what was going on. Sorry about that.
And become an actual rather than a virtual particle. Now, if you're watching this process from a large distance away, it looks like the black hole has emitted a particle, has emitted
I missed all your messages.
energy. And even with mini black holes, that has to be energy.
Yeah, so another workout session.
It looks like the black hole has lost mass and has lost energy. For some black holes, if they're not actively accreting, they start to lose mass. And it's particularly acute if you've got a tiny black hole to begin with. And so in practice, any mini black holes are expected to completely evaporate away quickly by this Hawking radiation process. Again, I want to stress it's a lovely idea, but it's not something where we've actually observed any of this kind of mission. This is just something that we would expect to happen.
Tom Moore on Facebook, he says if fire needs air, sun gets air to burn.
Well, this relates to quite an interesting puzzle which really baffled 19th century astronomers, which was where on earth the sun gets its energy from. Now, initially we thought that maybe the sun was a burning ball of gas, as Tom suggests. We know now, as Tom says, that it doesn't burn chemically. But even if it did, you can work out how the energy would be released by burning a ball of, say, methane gas of the mass of the sun. And it would be a matter of how the sun's chemical velocity for only a few thousand years, which is a real problem because we know the sun is 4 million, 5 million years old. So it must have some much more efficient mechanism for getting energy out of its mass. So the next idea that people thought about was perhaps the gravitational collapse of the sun, which was releasing energy. And it turns out that's a much more efficient mechanism. You can power the sun for a few million years using that mechanism. It's actually a very good model for the first few million years of the sun's life before some other process clicked on to power its current. So it was only in the 1920s that we really came to understand how the sun currently gets its energy. And this is from a process called nuclear fusion, by which hydrogen atoms are compressed together at very high temperatures to the point that the nuclei of the atom can actually stick together to form helium atoms. So rather than burning this hydrogen to form molecules, you're fusing it together to form a different atomic element, helium, and that releases a huge amount of energy, and it's what fuels the sun's velocity for the 5 billion years.
There you go, Tom. I hope that answers your question. Andrew, just one last one. This is from Father Jerry Drummond, and he wants to know how fast the universe is expanding.
Well, things move apart faster according to how far apart they are. So if something is 2 times further away, it'll also be moving away at twice the speed. And for that reason, when we talk about the expansion of the universe, we quote it as a kind of percentage per unit time. So what that means is the fraction of the distance that's added on for every year, for example. So in that vein, the current rate of expansion of the universe is 0.0000007% per year. And to turn it something concrete, it means that if you took 2 objects in outer space separated by 1 meter, then 1 year later they would be separated by 1.0000007 meters, and that means they're zooming apart at a speed of 0.002 femtometers per second.
He also says that presumably there will be a limit. What will happen when we reach that limit?
Well, in fact, there's no limit to how fast this percentage per year can be, and you can see that sits slightly uncomfortably at first with something that we're very used to in physics, which is the speed of light being an absolute speed limit for the universe. If the universe is expanding quite slowly at the kind of rates I've just been taking, then if you look at objects far enough away, then if you multiply the distance of the object by this tiny percentage, you can still contain an overall speed that's larger than the speed of light. And at first that seems very odd, but in fact it's exactly right. And it means that when you kind of rephrase all this into the mathematical language of Einstein's general relativity, that object that you're talking about is actually beyond what we call the cosmological horizon. And that in turn means that it's completely invisible to us. So it all does kind of work out in the end. But there's some subtleties.
Andrew Ponson, Dominic Ford and Karen Crawford discussing your space science questions. If you've got something you want to tackle, get in touch by email to astronomy@thenakedscientists.com. And that's all we have for this Naked Astronomy podcast. We'll be back soon with more space science news, interviews and questions. If you'd like to subscribe to the Naked Astronomy podcast, you can search for us on iTunes or join us at nakedscientists.com/astronomy. Naked Astronomy is produced by me, Ben Valsler from the Naked Scientists, and it comes to you from Cambridge University with support from its 800th anniversary team of Science and Technology Facilities.
There's always a choice. You can choose the chaos of outdated technology, fuel uncertainty and being over a barrel.
So on.
Or you can choose Polestar, 100%
Building.
electric. See the financial year offers at polestar.com.
Building something? What are you saying? AI viewers? No, I don't think I have any AI viewers.
So you've left your tax to the last minute. Now you're cramming admin, GST, EOFY, OMG, you didn't invoice that job in May. All paperwork, swing ticket, faded receipts, trying to match bank statements, missing deductions, lying awake at 2 AM, wondering if it's too late to become a kid on YouTube who just opens toys for a living. Solo by MYOB, Tames Admin, 365 days a year, so you never cram tax again. Do less work with the all-in-one admin app. Now $12 for 12 months. Sign up at MYOB.com. A subscription only, T's and C's apply.
Thrusting space science into the audio dimension. This is Naked Astronomy.
On the Naked Astronomy podcast this month, the International Space Station celebrates its 10th year of human habitation. That's a decade.
If you're viewing on Kick, I can't see, I gotta walk behind the camera to see your comments, but if you switch over to YouTube or Twitch, I can see your comments on the iPad there, so come party over there, I guess. Or have fun on Kick. I mean, I don't really watch Tikio Sam on Kick, but I think he's simulcast between the two anyway, like I do.
Lead-ion collisions in the LHC, the youngest galaxy ever detected, the light from which was emitted less than 600 million years after the Big Bang. I'm Ben Valsler from the Naked Scientists, and this is Naked Astronomy.
Supported by the STFC and Cambridge University's 800th anniversary team, this is Naked Astronomy. For more information, look us up online.
Welcome to the world's worst channel, where I review industrial cafes.
Yeah.
More information, look us up online at nakedscientist.com/astronomy.
As always, I'm joined by Karen Crawford, Andrew Ponson and Dominic Ford, so let's kick off with a roundup of this month's space science news. Dominic, what do you have for us?
Well, this is a paper presenting the latest results from the Galaxy Zoo project, which you may recall Chris Lintop talked about on this podcast back in April. This is a project which invites anyone who wants to visit the Galaxy Zoo website and to look at images of galaxies and to classify what these galaxies look like. And it means that Chris and his colleagues get a fantastic catalogue of the appearances of galaxies, and it means that visitors to the website get this awe-inspiring sense that they might be looking at galaxies that no human eye has studied in detail before them.
It's a wonderful example of the citizen science, isn't it?
Exactly, yes. Now, in this latest study, visitors to the website were asked to look at spiral galaxies and to say which ones have bars in their centres and which ones didn't. Now, going right back to the 1920s, when Hubble invented the galaxy classification scheme that we still use, it was clear that some spiral galaxies had smooth distributions of mass in their centres, and some of them had these strange bar-like features across their centres. And we don't really understand how these bars come about. But what's fascinating is that in this latest Galaxy Zoo, it's quite apparent that spiral galaxies with bars are statistically more likely to have red colours, and those without bars tend to be bluer. And that indicates that the bars of spiral galaxies have older stars in them, and that there's more young stars in the unbars spirals. So that suggests that whatever process it is by which these bars come about is also related to the processes that lead to the formation of stars in the galaxies. And that's potentially interesting for our own Milky Way, which we think is one of the galaxies that has a bar. And if you're interested in that research, it's by Carol Masters at the University of Portsmouth, and it's accepted for publication in the monthly listed at the OAS.
Thank you, Dominic. Carolyn, we're going to move away from normal astronomy a little bit here and towards...
No, it's only about... It's only about 10, quarter past 8 here in Australia. So not really too late. Sometimes I get home from work. Like last night I got home from work at midnight and came out here and just did in half an hour legs, mainly just leg extensions, hamstring curls. So this one's not too late.
We do this not because it's recreating the Big Bang, as has been alleged in some of the media,
But it's more that we can study some of the physical conditions of this big.
This is not a basement. This is an attic. This is actually a space above my garage. So,
interacting with each other. So you've got this kind of this
and equipment.
atomic particles. And this is
I bought most of this
study experimentally, something we can
in
only
the.
theory or simulations on. But the fact you have these
I bought most of this in the mid-90s. So I've had this gear for quite a long time. You know,
it's not just antimatter because we've created antiparticles like anti-electrons.
Oh yeah, it's early in the morning. So yeah, what's that? That's
it is an anti-atom. So it's
what are we? What, 9 hours ahead? 10 hours ahead?
But they're able to trap it and hold it for about half a second. Now, this may not seem like a big deal, but antimatter usually completely annihilates instantly. And so the fact that you can hold it and trap it holds the promise that we're going to be able to do experiments.
I can't remember. I think I paid like under $1,000 for all these back in the 90s. So it'd probably be a lot more now.
Thank you, Carolyn. Andrew, what have you spotted for us this month?
And the gym I go to for like heavy lifts with a partner, they don't allow filming at all. I mean, I've done, you know, when it was quiet, when it was just me and one other guy in there, I did a bit of, I filmed a few exercises. But yeah, I go there like on a Friday. No, it's not hot here at all. I mean, it's winter. What's the temperature at the moment? About 10 degrees Celsius at the moment. So it's not that hot. We're going into winter. Does it? What? No, June. June, July, August. No, it is winter. It is winter now. It's just, I mean, well, I guess it hasn't been too cold for winter yet. I'm still walking around in a t-shirt during the day. But then again, I'm one of those guys. You know, you see that guy walking with shorts in winter? I'm one of those guys. Yeah, so I've got the chat working now, so I can see your comments. I usually try to get out here at 6 in the morning. So that'd be what? Will it be 10 or 11 p.m. your time, the UK time? But I got back. Since I got back from Japan, I just haven't been really that enthused in working out again.
So lots of little events that you might expect in star formation would give you a rough image to little explosions rather than one big event.
Yeah, it would be much more staggered release of energy rather than these huge bubbles were just released from one event.
Thank you very much. Dominic, if we can come back to you, we've had a new mathematical idea, a prediction of how many Earth-like planets there should be around other stars.
That's right. Now, we've often talked on this podcast about extrasolar planets. These are planets talking about other stars. And to give an idea of how this field has grown in the last few years, the first exoplanet was discovered in 1992. There have been over 490 discoveries, and we can probably expect 500 discoveries from sometime in the next month. But all these planets which have been discovered are more massive than the Earth, and most of them would be rather more like Jupiter than like the Earth, and certainly not habitable planets where we might be able to see life. And the reason for that is simply that they're easier to detect. They're more massive, and these planets are normally detected by the gravitational influence of the Earth on their parent stars. And if a planet is more massive, it's a bigger effect which is easier to observe.
This is where you see the star itself wobble because it and its associated planets are around a central mass.
That's right. So there's been a lot of anticipation of when the first truly Earth-like planet might be seen to be the wobble it would exert on its parent stars. And we probably don't have to because we've talked on this podcast about the Kepler spacecraft staring at over 100,000 stars. And in the next few years, that will probably announce the discovery of Earth-like planets. But this month, an interesting interesting study was published in the journal Science, which had studied 166 stars around with 34 planets were found. Some of these were already known, some of these were new discoveries. And in this study, the masses of these planets were calculated. And it was found among these planets that low mass planets were more common than high mass planets. Some of these planets were only 3 or 4 times the mass of the Earth. And these low masses were seeing more planets than at 10 and 20 times the mass of the Earth. So on those grounds, these statements fit. There's an previous time will be announcing the discovery of somewhere between 120 and 260 planets. So that's quite a fascinating prospect for the future. And that's a paper by Andrew Howard from Berkeley, and that was published in Science.
So why is it important? Why should we care about finding Earth-sized planets? Because surely we're interested in all the other planets as well.
Well, of course, these planets have atmospheres, and once we start being able to get spectra of these planets, we can see what kind of atmospheres they have, and whether they have any trace molecules that suggest there might be potentially life on these planets.
Thank you, Dominic. Andrew, if we just come back to you, we've discovered the youngest galaxy ever detected. Tell me more.
That's right. In fact, there are 2 different ways you can look at it, either as the youngest or the most distant, because the further we look, the younger the objects are that we see. And the reason for that is just that although light travels very fast, it doesn't get to places instantly. It travels at a certain speed, and like anything else, the further it has to travel, the longer it takes to get there. So if you look at very distant objects, the light has to travel an extremely long time before it manages to reach you. So you are seeing those objects as they were. Their light, which was those galaxies were extremely young. So the news for this one of the most distant galaxy detected yet, and it comes from Matt Leonard and his team in France. They've been using ESO's very large telescope to look for a galaxy that was previously spotted. So when the galaxy was there, it was spotted by the Hubble Space Telescope. And this galaxy has the name UPHY 3813559. They've been targeting that galaxy with the very large telescope, and they've been looking for a particular feature in its spectrum. Its spectrum is just the breakdown of the different colours from that galaxy. They've been looking for something called Lyman alpha emission. The reason you look for very specific features in those spectra is because you can use those to know very accurately how much that light has been stretched since it was sent out. Light gets stretched as it comes through the universe, as the universe is expanding and stretching. So you work out how much the light has been stretched, and from that you can put a distance on the object. So the stretch factor for this object is almost 10. It's a redshift 8.6, and that tells us that the light has been travelling for something like 30 billion years. In other words, the universe was just 600 million years old at the time the light left the galaxy. And so that, if this detection turns out to be correct, is in fact a record holder for the most distant, the youngest object detected yet.
So I'm curious about if this detection is correct.
Well, for what it's worth, I think it's probably is correct, but there are plenty of people out there who cast slightly doubt on this. When you're looking for these very faint, very distant galaxies, there's always a risk because
It's too close to the wall.
You're working against noise that comes about from air, for instance, addition of an atmosphere, which can confuse you thinking you've seen something that's not there, or just noise in the detector where fluctuations lead you to think that something's a bit whereas actually it's not that. So there is some skepticism. There's to show that actually this is too strong. And also, for me, is detected this object in this estimated using information comes from the Hubble Space Telescope, which is what redshift this object should be, and got the same answer. So for me, the way that all this fits together suggests that it is a genuine detection.
And it's true that there may be other ones in the deep field that may be at a similar redshift, and presumably they're going to follow those up as well.
Oh, sure, yes, they're trying very hard to find more of these, and no doubt the rate will continue to increase.
Thank you very much, Andrew. We will put references for all of these stories online at thenakedscientists.com/astronomy.
Expand your mind and navigate Naked Astronomy, the stellar space science show. For more episodes of this program, look us up online at nakedscientist.com/astronomy.
This is the Naked Astronomy podcast with me, Ben Valsler, with Karen Crawford, Andrew Thompson, and Dominic Ford. And now a very new feature for Naked Astronomy. It's so new,
this
that
cable's
it doesn't yet have a
deteriorating.
name. If you've got any ideas, let us know by email. That's astronomy@thenakedscientist.com. But what it is a fast and furious roundup of facts and figures.
All the plastic covering from the cables coming off. It's like I said, I bought this in the 90s, so it's 30 years old. So it's bound to start deteriorating at some point.
Mine is 125 degrees C.
Saturn is made up mainly of hydrogen and helium, except for a solid core of rock and ice with 5 Earth
Yeah.
masses.
The density of Saturn is lower than the density of water on Earth. It would float very rapidly if you could find a pool large enough to hold it.
Its radius is 6,300 kilometers more. 6,300 kilometers more at its equator than at its pole.
Velocities of over 1,000 miles an hour at the equator.
This means we're first
thick atmosphere.
Titan has a rainfall cycle with clouds, rivers, and lakes. Not of water, but of methane.
And we know that because Titan is the furthest celestial body in which we've managed to land a spacecraft.
Saturn's moon Mimas has an impact crater that stretches across a third of its surface. If there were a crater of an equivalent scale on Earth, it would be wider than Canada.
Saturn's ice ring Enceladus reflects almost 100% the sunlight that strikes it.
And ice jets erupt from under the icy surface of Enceladus and eject water vapor, gas, and grains of ice into space, hundreds of kilometers above the Earth's surface.
So these ice geysers produce Saturn's faint but extended E ring.
Saturn's moon Iapetus has one face which is almost white as snow, and another as dark as coal.
There are even more factoids on our site at thenakedscientists.com/astronomy. But if there's a topic that you would like to get the high-speed lowdown on, do get in touch. astronomy@thenakedscientists.com. We'll be celebrating the 10th anniversary of human habitation on the International Space Station soon. But first, Andrew, a question from Matthew Parker. He wants to know what would happen if you get sucked past the event horizon of a black hole and then the black hole evaporates.
Well, I think this question has to win an award for about hardest question we've been asked so far on naked astronomy. We can recap quickly because we've spoken about black hole evaporation, I think on the previous podcast. In classical physics, a black hole just sits there. So once you've thrown enough matter together into a small enough space, you've created a black hole, a region of space where the gravity is so strong that light can't get out. The black hole just sits there. It could get larger by throwing more stuff in, but it could never get any smaller. But what Stephen Hawking realised is that quantum physics changes. When you add quantum physics, it slowly evaporates. And if you leave the total isolation without a trace, now the question is, jump into the black hole just before it evaporates. Do you somehow get back out? Do you somehow trip through a black hole? So nobody really understands this process in enough detail to give you a straight answer. It relates to something called the information paradox, in fact, which ultimately is not going to be resolved until we have a fully functioning theory of quantum gravity. This is perhaps one of the greatest challenges for physics in our generation. And although we have some ideas about what a theory of quantum gravity might look like, they are just ideas, so we can't come up with definitive answers at the moment. So all I can really say at the moment is that you can look at, in our current descriptions, mass does leak out of black holes. And one way of thinking about this process is through something called pair creation, where particles, even in a vacuum, little particles are constantly popping in and out of existence. And so even if there's nothing at all in a box, if you look close enough, you'll see tiny particles of matter and antimatter constantly being created. And then they come back together and they annihilate. And so overall, it's as though they were never there. Whereas if you think about that process right next to a black hole, what can happen is that one of the particles will fall into the black hole and the other particle can escape. Because if one of them happens to be thrown into the black hole, it can never come back to the one that's outside the black hole by the definition of a black hole gets out. So what happens is, say, if the antimatter falls into the black hole, it annihilates the matter inside the black hole. The matter part of that pair of created particles escapes into the normal universe, and it's as though the matter had actually escaped from the black hole. But if you're inside the black hole, what you actually find is that you're slowly being blown away by these antimatter particles screaming in you. So it's not like you yourself really get out of the black hole. The total mass that made you up does get out of the black hole, but it doesn't really look like the semblance of the human being that is you does get out. So I don't really think this is a practical mechanism for surviving a trip. Until it does.
The black hole does evaporate, it's still not happening. Let's carry on. We've had one from LH Collision. What's the from the side? Why galaxies? Any spherical?
Well, yes, first of all, not all galaxies are flat. In fact, the majority of the systems are spherical or ball-shaped galaxies, really not completely elongated, and these are no practical. Now, we tend to sometimes forget that there's spiral galaxies. They tend to grace the coffee table astronomy books quite so much as all the beautiful spiral galaxies out there. But spiral galaxies are flat or disc-shaped because they are rotating, and this is the key thing. It's a system of things rotating, whether it's stars or gas clouds. And early on, this rotation means you've got all these things jumbling together. There are going to be collisions. And collisions between objects act to average out their speed and their velocity. So if everything's rotating the same way around the centre, the collisions don't actually affect that forward motion. But the collisions will act to average out the vertical velocity. So things moving really in and out of this disk. And through all the collisions, that component will get averaged out to zero. And so things will flatten out. And this is a characteristic we see in many rotating systems, whether it's planetary disks, the cocoons that go on to form planetary systems. Planetary systems are all in a flat disk around their host star. Or spinning systems, we just have that in our factoid explosion. These are all spinning systems where the collision's been averaged out and you end up with a very, very flat system.
Thank you very much. And thank you for your question, LH Collision. Of course, if you'd like to get in touch with us via Twitter, you can get in touch with all of the scientists. That includes us here at Naked Astronomy by tweeting at Naked Scientists. We'll be answering all of your questions later in the show. But now, the International Space Station has been inhabited for a decade, and it's allowed us to undertake research that would formerly never be possible. I spoke to Kelly Humphreys from NASA's Johnson researching the physiological impact. What impact does it actually have on the body to be in orbit for 6 months?
Well, I'm going to simplify this. There are a lot of different impacts. But some of the chief things that we struggle with is trying to make sure that we don't have bone and muscle density loss. Your body, when it does not have gravity pulling down on it, tends to atrophy, especially your lower limbs, your legs, your feet, legs. And so what we do is try to do countermeasures in which we have various pieces of exercise equipment on board. We have stationary bicycles, we have treadmills that pull you down on the course so that you try to approximate one gravity on your football, which is what we're learning really makes a difference in whether or not you have bone density loss, which is serious, similar to what folks on Earth that get osteoporosis deal with. Muscle density loss, we combat that with rigorous exercise on what we call the advanced resistant exercise device, which is essentially a set of stretchable cables, and those allow them to mimic the effects of weightlifting, even in the absence of gravity that would allow you to do it for real.
So obviously understanding how life copes with that environment is very important, but it's not just human life that's been looked at. I've been to very interesting experiments on plants. How's the process of that?
You know, we're looking at a variety of different things on plants. There's an experiment out there right now that is looking at the relative importance of acidity of water and
I was going to do like another Monday meal prep today, but then because I was busy on at work on the weekend, I didn't go grocery shopping to collect the ingredients for the next thing I wanted to make. So therefore, I'm doing a workout stream instead today. Not really a big fan of cooking, so that's why I don't really want to do cooking streams, but I kind of got a meal prep anyway, so I thought if I got a meal prep, I may as well stream, but yeah, didn't go grocery shopping, so today wasn't like exactly the best food. No. Last two sets.
Are learning a lot about humans, about life in orbit, and about how we cope with those conditions. But can we also use the space station to probe the
working out a lot longer than I
expected
to.
Astronomy there?
Last two sets.
On the special mission that's scheduled to go up in February, we're going to be taking the alpha magnetic spectrometer, which is developed by Massachusetts Technology, and we're going to install that on the space station and begin looking for dark matter, which is considered to be one of the most prevalent substances in the universe, but it's very hard to track. And we're working with scientists around the world to develop a very advanced instrument capable of running for a decade, try to get a good handle on exactly how much dark matter is in the how it affects the matter that we're all familiar with in the universe. In that respect, the space station is getting ready to become a tool.
This is explaining how the ISS has been for 10 years and is now moving forward into a new phase of
Just the idea of having someone in space just oh my god, that can't be anything worse.
It's certainly bad enough down here with gravity, let alone being trapped in a small metal can above the Earth with horrendous food poisoning.
And no privacy whatsoever.
Of course, it'd be terrible. Speaking of humans living in zero gravity, we've had an email from Aaron Thomas. Dominic, I'll put this one to you. He's asked if there's a region of zero gravity in the centre of the Earth.
Yes, that's right. At the centre of the Earth's mass is distributed all around you, and that means that the gravitational pull from each part of the Earth's mass is pulling you in all different directions and those forces cancel out to leave no net gravitational force on them. So the centre of the Earth, you feel no gravitational pull. That's only completely true exactly at the centre of the Earth. If you move slightly to one side, then there's slightly more mass on one side of you than on the other, and that means you'll feel a slight force pulling you back towards the centre of the Earth. Now, you can mathematically work out how the Earth's gravitational field changes with depth, and the answer turns out to be that the gravitational pull is proportional to your distance from the centre of the Earth. So, for example, if you're 10% of the way out from the centre of the Earth's surface, you feel about 10% of the gravitational pull that you feel here on the surface.
Alright.
There is a large volume of space inside the Earth where gravitational force is much weaker than what we're used to on the surface.
But assuming that even all of the gravity from Earth itself cancels out in this one place in the centre, would you still feel the pull of the Sun and the Moon?
Yes, you would still feel the pull of the Sun and the Moon. And in fact, we on the surface feel the
Alright,
pull of the
last
Sun and the Moon.
set.
We're not used to the sun rising east and us all feeling pulled to the east and the sun setting in the west. And that's all pulled to the east and the sun setting in the west.
Last set, then I'm done for today.
And the reason for that is that the Earth is in orbit about the Sun. The Earth is in free fall towards the Sun, and that's putting it in orbit once a year about the Sun. And thankfully, we are also in orbit, so we stay on the Earth going around the Sun every year. Now, if you were at the centre of the Earth, you would likewise hope to be in the Earth's orbit in free fall generally towards the Sun, and that means you would not appreciate the force because of that easily. So if you were sat there at the centre of the Earth enjoying your gravity, you would just float there at the centre of the Earth.
I actually enjoy the centre of the Earth. I get it quite hot on there.
So you might need a good spacesuit.
We've had an email from Gordon Kubek. He believes that the speed of light is really an absolute speed. In particular, he's asking about the way that we use something as a reference point against.
Yeah, it's a good question, because speed, of course, is what used in physics classes is supposed to be relative. It's especially clear in space, for instance. If you imagine a spaceship moving past a planet at something like 20,000 miles per hour, then in space, where you've got nothing else to refer to, that's actually indistinguishable from the spaceship staying where it is and the planet moving past in the opposite direction at 20,000 miles per hour. And it's absolutely right that physics does tell us that those two things are indistinguishable. So I think what this question is getting at is that since the actual speed that you assign to an object depends on what reference points you use for assigning that speed, how can there be a speed limit? Now, the key to answering that question is recognizing that in physics, 1 plus 1 does not equal 2. In fact, 1 kilometre per hour plus 1 kilometre per hour actually equals 1.99999. I don't have to do that again. 1.99999999999 kilometres per hour. So it's very close to, but not quite 2 kilometres per hour. And this odd rule of addition comes about from something called Einstein's special relativity, which actually starts from Einstein's insight that experimentally we found that the speed of light is always the same, regardless of what speed you happen to be moving at, and then tries to move beyond that and incorporate these ideas of how speeds can be relative.
Alrighty.
And the inevitable conclusion of that is that, as I say, 1 plus 1 does not equal 2, and if you keep increasing your speed in increments of, say, 1 kilometre per hour...
Alrighty, that's today's workout done.
From your point of view, that each time you're getting faster...
Usually I just do 6 warm-up exercises and 6 actual weighted exercises, but today I did a few extras because I wanted to focus more on my back. So I did a few extras, but that's about it for today. I'm tired, gonna go finish my dinner and then head to bed early, I think, today. Good night.